Strong acids. There are only 3 of them. Dissociate 100% in aqueous solution. Let me show you what that means. Here's my first example. HCl is a strong acid. You have seen in the simulations that it can transfer a proton from HCl to water, producing H3O plus and a Cl minus ion. 2 ions are formed. This is one way only. One way reaction. Exclamation point. 100% here. That means none of these. No HCl remains. In the bottle that's labeled HCl, there is no HCl. It's all H3O plus and Cl minus. Second example, I'll just use HNO3 here. Sometimes the water is not written. It's simply done this way, where you say H plus AQ, NO3 minus AQ. Again, 100% is ionized. There is no HNO3 in the bottle that's labeled HNO3. Weak acids are completely different. A weak acid will make an equilibrium in aqueous solution, a balance between the dissociated and associated states. Here's my example. HNO2 is a weak acid. Draw along with me. Nitrogen makes 3 bonds, rule of Honk. Oxygen makes 2 bonds, rule of Honk. There's nitrous acid, HNO2. It can dissociate. If it does so, the H plus will be an ion. It's actually H3O plus. NO2 minus will remain as an ion. Also aqueous. This original molecule is aqueous as well. This is not a salt where the salt is dissolved, the bond is dissolved. This is a weak acid. It's dissolved, but it is still together. To represent the equilibrium, draw a second arrow. These ions do get back together. You saw that in the simulations. They get back together and form the original molecule. There is therefore a balance between associated and dissociated. It's not 100% this, it's not 100% this. It's some other balance between the 2 states. Sometimes it's not written as pictures. If it were not written as pictures, this is how it would be shown. HNO2, H plus, NO2 minus. Everything's aqueous here. 2 arrows. Whenever you see the 2 arrows, there'll be an equilibrium formed. So if you recognize there is a balance between the 2 states, then mathematically it becomes important to say, what is the balance? Which way does it tip? Which way does it tip? Is it mostly ions? Is it very few ions and mostly together? One way to do that is with percentages. We can say what percent is in this dissociated state. Here's my example. 1 molar, if we had a 1 molar solution of nitrous acid, HNO2, it would be 2% dissociated at equilibrium. At equilibrium. A 1 molar solution of HNO2 is 2% dissociated at equilibrium, period. what this means. Let's go back to the chemical equation. HNO2, aqueous, will be partly in the ionized state and partly in the unionized state, the associated state. Partly ions. Solution of HNO2 will be partly in the ionized state and partly in the associated state, which is not ionized. We can now say, according to the words above, 2% of the molecules will be dissociated, meaning 98% are not ionized. This is a way of expressing the balance. For HNO2, 1 molar solution, this is the balance. If we change the acid, if we change the molarity, the balance will shift. We would have a different percent dissociation if we change the acid or if we change the molarity. Number 4 talks about a different way to express the balance, to express the equilibrium. And it's using a Ka expression. This K will stand for an acid dissociation constant. Let me give you an example. We'll use the same example as above. So we have HNO2, a weak acid, which can dissociate into ions, but these ions can reassociate because it is a weak acid. Now, Ka is going to be a ratio, a mathematical ratio. And it's going to put the dissociated species on the top of the ratio. So it's something on the top, something on the bottom. I'll write it in words first. Dissociated on the top. Associated on the bottom. Now specifically, this now becomes mathematics. H plus and NO2 minus are the dissociated species. They're going on the top in brackets. And the brackets, these square brackets here, indicate the molarity of that species. So the molarity of this ion, the molarity of this ion. It is multiplication on the top. If you need to write the little dot or little X, you can do so. Real chemists don't do that. They just put them side by side. Oop, made a mistake. This is a 2, not a 3. 2, not a 3. HNO2. And on the bottom will be the associated form, the HNO2 right here. So here's the dissociated on top, associated on the bottom. That ratio will be a value. It's like a fraction. Maybe it's 1 out of 4. Maybe it's 1 out of 2,000. We're going to calculate that given this equilibrium right here. So using this 2% dissociation, it's 2% of 1 molar. So we can say at equilibrium, the molarity of the H plus is 0.02 molar. 2% of the 1 molar solution. The NO2 minus is equivalent. 0.02 molar. For every plus, there's a minus. For every H plus, there's an NO2 minus. These are equal. On the bottom will be the 98% that is associated. 98% of 1 molar is 0.98 molar. Alright, so this I'm going to run through my calculator and solve. It's a ratio. It's not as simple as 1/4, but I can solve this with a calculator. On the calculator, I am doing 0.02 times 0.02 divided by 0.98. And here's my answer. I'll express this in scientific notation, which is the way almost always Kas are expressed. It is 4 times 10 to the minus 4. So if we look at this now in its entirety, this is a Ka value. And what makes it valuable is that it is a constant. So it's a Ka value for HNO2. It works at any concentration, any molarity of HNO2. This Ka will always be the same value. The ratio when you calculate it out will always be this number. Percent dissociation will not be a constant. If it's not 1 molar, it'll be a different percentage that's dissociated at equilibrium. But Ka is invariant. So the last one talks about using Ka values comparatively. Each acid has a Ka number, a Ka value that describes its dissociation. Some numbers are bigger than others. That's what it means comparatively. So let's take a look here. First, formic acid. First, write the dissociation with me. The H plus can come off, this H plus right here, leaving you with trigonal planar geometry. Draw the angles well. These two ions, H plus and formate ion. There's a Ka that describes that. That has this value, 2 times 10 to the minus 4. That's the Ka value for formic acid. It equals that ratio. Dissociated, I'll write it this way, HCOO minus represents this ion here over the associated HCOOH. So that describes the equilibrium for formic acid in an aqueous solution. Now I'm going over to the other side to nitrous acid. You've done this before, so this should be easy. H plus and O2 minus. Ka we've seen before, 4 times 10 to the minus 4 equals the ratio of the dissociated ions to the associated HNO2. So now we can compare. You can see they look very similar, the expressions. The only difference is what is the negative ion, really. That's the only difference. But the numbers are also different. We have 2 times 10 to the minus 4 here. We have 4 times 10 to the minus 4 here. What that means is that this ratio has a larger numerator. I'm just going to say it this way, more on top of the fraction. That's why it's a bigger value. So that means there's more ions in the HNO2 solution compared to the formic acid solution. So we can say with confidence, bigger Ka, greater dissociation. I'm going to write it this way, greater degree of dissociation. A larger percentage dissociation. More ions. And that means a stronger acid. So bigger Ka, stronger acid, greater degree of dissociation. So this is why chemists love Kas. You can compare different acids to each other. You can do mathematics to figure out the exact molarity of different ions. It is a powerful tool, so you want to learn how to use them.